Hello, everyone. My name is Carlos Duarte, and I'm a CBE researcher. And today I'm going to present a project that we did in collaboration with two industry partners, TRC and Taylor Engineers, and also along with folks at the LBNL lab. New building controls are being developed and improved every single year. This includes controls in ASHRAE Guideline 36. This document contains specifications on how to control heating, ventilation, and air conditioning to achieve high energy efficiency without compromising occupant satisfaction and health. And CBE and industry partners have field demonstrated some of these controls and found that the energy savings range from as low as 4% all the way up to 60% and have a payback period that is usually 10 years or less. But a payback period of 10 years or less might be surprising to hear, but implementing new controls in buildings is quite a challenge because almost everything about a building is non-standard. So it's currently a challenge to deploy or implement any plug-and-play solutions. But that is changing as we demonstrate through this field demonstration. We still want to learn how the latest control strategies perform in real-world operations. So the main objective of this study is to quantify the energy savings potential of water-side sequences found in the latest edition of Guideline 36. However, another objective of this study is to deploy these controls using the latest standardization methods. We want to learn more about how we can stitch all these methods together to reduce the effort of deploying new sequences in a building. And the funding for this came from the California Energy Commission and through the Department of Energy. So like I just mentioned, we have the objective of deploying these control strategies using standardization methods. And the first one is ASHRAE Guideline 36, and which I just said, this is a document that contains a set of high-performing sequences or strategies for HVAC systems. They detail in English text how the strategy is supposed to work, the inputs needed, and the expected outputs. And they were created by control experts so that the building designers can pick and choose from a library that best suits their building or mechanical system needs. So they don't have to write their own custom specifications for a new building. So that is the first piece of standardizing the controls deployment. The main issue with this is that it's just text. And at least for now, we can't directly use them in building automation systems for building control. We need to translate this text to a program that computers will understand. And this is where the control description language, or CDL, comes in. CDL and the Open Building Control Project at LBNL aims to simplify the design and implementation of building control sequences. And ASHRAE 231P is reducing the need for control vendors to independently program their interpretation of high-performing sequences, reducing costs and they're prone to errors. So that is the second piece of this puzzle. And control sequences need specific inputs and write specific outputs back to the equipment they are controlling. And currently, this is a huge undertaking to identify and map all the points needed by the control sequences. And this huge effort may be repeated multiple times throughout the life of the building by multiple entities, because like I said, building controls are being developed every single year or improved. Ideally, we want to go through this point mapping process once and deposit all our knowledge gained from this point mapping exercise in a tool that can be reused over and over again. Well, this is where the BRIC ontology comes in. BRIC provides a standard framework for data organization, identification, and associated properties with it. All of this information is encoded in a computer in a way that computers can understand. So that is, BRIC gives computer encoded meaning to the equipment, to the data they produce, and what is the relation to other components in the building. So I produced a BRIC model for our demonstration sites, and that was a big effort that took many months to developed because data sources are scattered all over the place. We got the building management system, we got drawings, and we even got knowledge from the facility manager that we need to identify in order to make our control systems or control strategies work. But now that I created this data model, other CBE researchers can piggyback off this data model and go directly into testing their new controls, like the ones that our graduate study is working on to streamline the retro commissioning process in the building. So this is the third piece of our puzzle. And the last piece is BACnet. So BACnet defines a set of rules that allows exchange of data information between the devices, equipment, and other systems that make the whole BMS. And so we are using all these standardization methods to serve as the building blocks to create high-performing, portable, and scalable control applications, which in theory allows us to develop an application just once and run it in multiple buildings. And that is one of the things that we're trying to demonstrate with these field studies. So we did this field study on several sites, and today I'm going to focus on Sardajada Hall, which is a UC Berkeley building here on campus that is 7 stories with a floor area of 141,000 square feet. It contains a variety of space types like offices, classrooms, and an auditorium, but it also contains a nanofabrication lab with 2 large clean rooms that brought on several challenges for our controlled deployments, because the same water plants were being used for both the nanofab spaces and the office spaces. So due to these constraints, the only control block that we were able to implement from Guideline 36 was the trim and response block. We implemented the Guideline 36 intervention in both the chilled and hot water plants. But today I'm just going to focus on the chilled water plant. The chilled water plant uses a water-cooled centrifugal chiller with 24-hour operation because of the nanofab. So there's cooling loads all the time in this building. And the trim and response modifies the chilled water supply set point, water supply set point, from 43 all the way up to 52 degrees, depending on the chilled water demand. So we started data collection in November, and we are still currently collecting some more. We are using the rapid MMV process data collection method that we presented in previous CBE meetings. With this method, we are randomly switching between the baseline control and the intervention to reduce the confounding factors such as changes in occupancy, operation, and weather. So in theory, we get at an answer much quicker on what is the savings potential of these control strategies. So this plot gives you an idea of the back and forth between the different control strategies. And the baseline control is set to maintain a constant 43 degrees Fahrenheit for the chilled water temperature. And the Guideline 36, like I said, is ranging from 43 all the way up to 52, depending on the demand. So here you see 2 plots with the same x-axis, which is the hour of the 24-hour day. The top plot is chilled water temperature, and the bottom plot is the water flow rate. And as expected, the baseline maintains a constant water temperature of 43 degrees Fahrenheit because that's what we define it to do. And looking at the water flow rate, it ranges from 650 gallons per minute all the way to 725 during peak condition. So let's compare to the Guideline 36 intervention. In this case, we observed an average of 3 to 5 degrees, an increase in the water temperature of 3 to 5 degrees Fahrenheit. And recall that the top of the range was 52, and we saw that it never got to 52 because the heat exchanger that serves the process cooling loads for the nanofab couldn't maintain their temperature, their set point of 65 if we go with chilled water temperatures higher than 48 or 49. So the trim and response block was finding an optimal temperature that was be able to satisfy all the cooling loads. So how do these differences affect the electrical consumption for the chiller? So we see that the operation for we see that the baseline operation The power consumption ranges from 70 kilowatts to almost 100 kilowatts during peak conditions. And for the intervention, we observed that there was a reduction of 10 kilowatts, which is pretty substantial for a chill water temperature, for a chiller water plant that is operating 24/7 due to the nanofab. So we were able to save some energy through this. So we are still collecting data and constantly running, updating our running average. And at the moment, we see a total power reduction of about 13.5 kilowatts, which includes the pumps of the chilled water plant. So which it represents 12% power reductions, which we're saving about $3,000 per month with just this simple intervention. So in conclusion, we saw that the brick model takes a lot of time to develop. So, and this is mainly due because data sources are scattered all over the place. And there's also questions on how do we maintain up-to-date brick models so we can get the latest information from them. But once we have these methods put together, we see that it brings on many benefits for the control retrofits. Mainly, we get consistent performance. We just write one application and can run in multiple buildings, which overall increases the cost effectiveness of deploying these control systems. And we saw that the ASHRAE Guideline 36 trimmer response adapted well to laboratory constraints. We saw small temperature increases for the chilled water temperature, but we got pretty good savings, which the amount to 12%. So we're still collecting data to build weather normalized models to figure out what is the savings potential for a whole year. And we're going to detail all of this in a report that is due by the end of the summer. So if you have any questions, I'll take them, and thank you.